Welcome to this rigorous scientific lecture on one of the most fascinating phenomena in everyday fluid mechanics, why ketchup refuses to move, and then suddenly pours all at once. You've experienced this countless times. You turn a ketchup bottle upside down, and nothing happens. You shake it gently, still nothing. Then suddenly, an enormous blob of ketchup rushes out all at once, ruining your carefully prepared meal. This isn't random behavior. It's precise, predictable physics. The question we're investigating today is, what fundamental material properties cause this peculiar flow behavior, and can we quantify it mathematically? To understand ketchup, we must first understand the fundamental classification of fluids. Let's start with Newtonian fluids. A Newtonian fluid is one where the viscosity, the resistance to flow, remains constant regardless of the applied stress. Water, air, and simple oils are Newtonian. The constitutive equation for a Newtonian fluid is tau equals mu times gamma dot, where tau is the shear stress, mu is the dynamic viscosity, and gamma dot is the shear rate. This linear relationship means that if you double the force, you double the flow rate. The viscosity mu is a material constant that doesn't change. Non-Newtonian fluids, however, have viscosity that depends on the applied stress or shear rate. Their behavior is far more complex and interesting. Here we see the flow curves. For Newtonian fluids, the relationship is linear. For non-Newtonian fluids, the curve is nonlinear, showing complex behavior. Non-Newtonian fluids can be classified into several categories. Let me introduce the two most relevant for understanding ketchup. Shear-thinning fluids, also called pseudoplastic fluids, become less viscous as you apply more stress. Paint, blood, and polymer solutions exhibit this behavior. Shear-thickening fluids, or dilatant fluids, become more viscous under stress. Cornstarch in water is a classic example. Ketchup is shear-thinning, but it also possesses another critical property that makes it truly fascinating. It has a yield stress. The yield stress is the minimum stress required to initiate flow. Below this threshold, the material behaves like a solid. Above it, the material flows like a liquid. When the applied stress tau is less than the yield stress tau sub y, there is no flow. The material remains stationary, behaving as a solid. When tau exceeds tau sub y, flow begins and the material behaves as a liquid. This binary transition is what creates the all-or-nothing behavior we observe. Materials exhibiting this behavior are called Bingham plastics, named after Eugene Bingham, who studied these materials in the early 20th century. The most accurate model for ketchup is the Herschel-Bulkley model, which combines yield stress with shear-thinning behavior. The equation is tau equals tau sub y plus k times gamma dot to the power n, where tau sub y is the yield stress, k is the consistency index, and n is the flow behavior index. When n is less than 1, we have shear-thinning. For ketchup, n is typically between 0.2 and 0.4. When n equals 1, we get a Bingham plastic with constant viscosity after yielding. When n is greater than 1, we have shear thickening, though this is rare in food products. This diagram shows the Herschel-Bulkley behavior. Notice the flat region below yield stress where no flow occurs, then the curved region showing shear thinning once flow begins. This is an excellent question. What gives ketchup its yield stress? The answer lies in its microstructure. Ketchup is a complex suspension of tomato solids in a continuous aqueous phase, containing sugars, salts, acids, and most importantly, polysaccharides. The yield stress arises from several microstructural features working together. First, tomato fibers, which are cellulose-based, form an entangled network throughout the fluid. This network can bear stress elastically up to a point. Second, pectin molecules, which are long polysaccharides, form hydrogen bonds with each other and with water molecules, creating a weak gel structure. Third, the tomato particles carry surface charges that create electrostatic repulsion, but at close range, these particles can form weak attractive bonds through van der Waals forces. Finally, many commercial ketchups contain xanthan gum, a bacterial polysaccharide that dramatically increases yield stress and enhances stability. Here's a schematic of ketchup's microstructure. The red circles represent tomato particles suspended in a green network of polysaccharide chains. This network can bear stress elastically. Now let's perform some back-of-the-envelope calculations to quantify ketchup's behavior. This is where the physics becomes truly concrete. Experimental measurements show that ketchup has a yield stress between 10 and 100 pascals, depending on the brand and formulation. Let's use 50 pascals as our typical value. So tau sub y approximately equals 50 pascals. Here's a practical question. What force must you apply to the bottle to make the ketchup flow? Let's calculate this precisely. A typical ketchup bottle has an opening diameter of about 2 centimeters, giving an area of roughly 3.1 times 10 to the minus 4 square meters. The area equals pi r squared equals pi times 0.01 squared equals 3.14 times 10 to the minus 4 square meters. The force needed is the yield stress multiplied by the area. Force equals tau sub y times A equals 50 times 3.1, 4 times 10 to the minus 4. This gives approximately 0.016 newtons, or about 1.6 grams force. That's remarkably small. You might ask, if only 1.6 grams is needed, why does it feel like you need to shake so hard? Excellent question. The answer lies in how gravity acts on the ketchup column. Let's analyze this carefully. When you hold the bottle upside down, gravity creates a stress on the ketchup, but this stress depends on the weight of the ketchup column divided by the cross-sectional area. The gravitational stress equals ρ, HO, GH, where ρ is density, G is gravitational acceleration, and H is the height of the ketchup column. Ketchup has a density of approximately 1,200 kilograms per cubic meter, slightly denser than water, due to dissolved sugars and suspended solids. Consider a half-empty bottle, where the ketchup column is about 15 centimeters high. The gravitational stress equals 1,200 times 9.8 times 0.15. This gives approximately 1,760 pascals. But wait, this is much larger than our 50 pascal yield stress. This is a critical question. If gravity provides 1,700 pascals, but we only need 50, why doesn't it flow instantly? The answer is that the stress is not uniform throughout the ketchup. The maximum stress occurs at the bottle opening, but in the bulk of the fluid, the stress is much lower. Surface tension at the air ketchup interface and the bottle's narrow neck create additional resistance. The ketchup must overcome not just yield stress, but also geometric constraints. Once the ketchup begins to flow, its shear-thinning nature becomes critical. Let's examine this quantitatively. As shear rate increases, the apparent viscosity drops dramatically. This is why once flow starts, it accelerates rapidly. The apparent viscosity equals tau over gamma dot, which equals tau sub y over gamma dot plus k times gamma dot to the power n minus 1. At very low shear rates, as gamma dot approaches 0, the apparent viscosity approaches infinity because of the yield stress term. At high shear rates, the yield stress becomes negligible, and the viscosity drops to very low values, making the ketchup flow easily. This graph shows how apparent viscosity decreases dramatically with increasing shear rate. At rest, ketchup has extremely high viscosity, but once flowing, it becomes quite fluid. Let me give you concrete numbers to illustrate this dramatic change. At a shear rate of 0.01 per second, which is barely perceptible flow, the apparent viscosity is approximately 5,000 pascal seconds. This is extremely viscous, like thick honey. At a shear rate of 10 per second, which corresponds to vigorous pouring, the apparent viscosity drops to approximately 5 pascal seconds. This is a 1,000-fold decrease. This dramatic viscosity decrease explains why ketchup suddenly gushes out. Once flow initiates, the resistance drops precipitously. Now let's apply our understanding to develop practical strategies for dispensing ketchup efficiently. Tapping the bottle introduces transient high stresses that locally exceed the yield stress, creating weak points in the structure where flow can initiate. Shaking creates oscillating stresses that can temporarily break down the network structure, reducing the effective yield stress. Storing upside down allows gravity to continuously apply stress, gradually weakening the structure near the opening over time. Inserting a knife breaks the gel structure mechanically, creating a low-resistance channel through which ketchup can flow more easily. Heinz famously recommends tapping the embossed 57 on their bottles. This location corresponds to the optimal angle and position for maximum stress amplification. Ketchup exhibits another fascinating property called thixotropy, which is time-dependent, shear-thinning behavior. When you apply constant stress to ketchup, Its viscosity decreases over time as the microstructure gradually breaks down under the sustained load. If you hold the bottle upside down and wait patiently, eventually the structure weakens enough that flow begins. But this can take many seconds or even minutes. After flow stops, the network structure gradually rebuilds through Brownian motion and molecular rearrangement. This recovery typically takes minutes to hours. This curve shows thixotropic behavior. Under constant stress, viscosity decreases over time as the internal structure breaks down progressively. Temperature has a profound effect on ketchup rheology. Let's quantify this relationship. At 4 degrees Celsius, typical refrigerator temperature, ketchup is notably more viscous and has higher yield stress. The yield stress can increase by a factor of 2 to 3 compared to room temperature, making it much harder to dispense. At 20 degrees Celsius, ketchup flows much more readily. The yield stress is at its typical value around 50 pascals. Higher temperature increases molecular mobility, weakening hydrogen bonds and reducing the strength of the polysaccharide network. The yield stress follows an Arrhenius-type relationship. Tau sub y of t equals tau sub y of t sub 0 times exponential of e sub a over r times 1 over t minus 1 over t sub 0. This temperature dependence explains why you should let refrigerated ketchup warm to room temperature before trying to dispense it. To put ketchup's behavior in context, let's compare it with other yield stress fluids you encounter. Toothpaste has a yield stress of approximately 100 to 200 pascals, about 2 to 4 times higher than ketchup. Mayonnaise, being an emulsion stabilized by egg proteins, has even higher yield stress of 200 to 400 pascals. Yogurt has a yield stress similar to ketchup, around 20 to 50 pascals, though it's less shear thinning. Paint has yield stress in the range of 50 to 150 pascals, designed to stay on vertical surfaces without dripping. Geological materials like mud and clay can have yield stresses exceeding 1,000 pascals, making them extremely resistant to flow. This bar chart compares yield stresses of various materials. Ketchup is relatively low, while materials like mud have much higher yield stresses. Understanding ketchup rheology is crucial for industrial production and quality control. Manufacturers use rheometers to measure yield stress and viscosity curves to ensure batch-to-batch consistency. Product specifications typically define acceptable ranges for yield stress, usually 40 to 60 pascals for standard ketchup. By adjusting xanthan gum concentration, tomato solids content, and processing conditions, manufacturers can precisely tune the rheological properties. Modern squeeze bottles with one-way valves are specifically designed to work with ketchup's yield stress, allowing controlled dispensing without air intake. I want to briefly mention an ongoing scientific debate about whether true yield stress actually exists. Some rheologists argue that there's no true yield stress, only extremely high viscosity at low shear rates that appears solid-like on practical timescales. Others maintain that yield stress is a genuine material property arising from jammed particle networks and percolating structures. For engineering and practical purposes, the yield stress concept works exceptionally well and provides useful predictions, regardless of the fundamental debate. How do we actually measure yield stress experimentally? There are several methods. In a stress ramp test, you gradually increase the applied stress and observe when flow begins. The yield stress is identified at the onset of flow. Apply a constant strain and measure how stress decays over time. If stress reaches a non-zero plateau, that plateau value is the yield stress. Measure viscosity at various shear rates and extrapolate the stress shear rate curve back to zero shear rate. The y-intercept is the yield stress. Different methods often give slightly different yield stress values because they probe different aspects of the material's response. Let's dive deeper into what happens at the molecular level during shear thinning. When ketchup is at rest, polysaccharide chains are randomly oriented and highly entangled, creating a strong three-dimensional network. When shear is applied, these long molecules begin to align with the flow direction, reducing entanglement and lowering resistance. Simultaneously, suspended tomato particles rearrange into organized layers that slide past each other more easily than the random initial configuration. Hydrogen bonds holding the structure together continuously break under stress and reform in new configurations, with the balance shifting toward breakage at higher shear rates. On the left, we see randomly oriented polymer chains at rest. On the right, under shear, the chains align with the flow direction, dramatically reducing viscosity. Here's an interesting question to consider. Given that ketchup is a suspension, why doesn't it separate into clear liquid and solid particles over time? The answer is precisely the yield stress. The gravitational stress from particle weight is insufficient to overcome the yield stress, so particles remain suspended indefinitely. Let's calculate whether a tomato particle can settle through ketchup. A typical tomato particle has a diameter of about 100 micrometers, or 10 to the minus 4 meters. The gravitational force on the particle is 4/3 pi r cubed times delta rho times g, where delta rho is the density difference. For our particle, this gives approximately 5 times 10 to the minus 10 newtons, an extremely small force. The stress this creates is force over area, approximately 0.06 pascals. This is far below the 50 pascal yield stress, so the particle cannot settle. This is why ketchup remains perfectly stable for months or even years without separation, unlike simple suspensions. The chemical composition of ketchup significantly affects its rheological properties. Sugar comprises 20 to 25% of ketchup by weight. This affects viscosity but not yield stress significantly. Salt at 2 to 3% affects the electrostatic interactions between charged polysaccharides, modulating the gel strength. The acetic acid from vinegar gives ketchup a pH of 3.7 to 3.9, which affects pectangulation and protein charge states. Even though xanthan gum is present at only 0.1 to 0.3%, it has an enormous effect on yield stress because of its extremely high molecular weight. Manufacturers must balance these ingredients carefully. Too much xanthan increases yield stress excessively, making dispensing difficult. Too little, and the product separates. Let's apply dimensional analysis to understand how yield stress scales with system parameters. For particle suspensions, theory predicts that yield stress scales with the volume fraction of particles, typically as phi squared or phi cubed, where phi is volume fraction. Yield stress is proportional to phi to the power n, where n is typically between 2 and 3. For polymer networks like pectin and xanthan, yield stress typically scales with concentration to a power between 1.5 and 3. Yield stress is proportional to c to the power m, where m depends on the polymer architecture and interaction type. Ketchup combines both particle and polymer effects, making its behavior quite complex and difficult to predict from first principles. The principles we've learned apply far beyond ketchup to many important industrial and natural systems. Fresh concrete has a yield stress that must be carefully controlled to allow pumping through pipes while maintaining shape after placement. Blood exhibits yield stress at low shear rates due to red blood cell aggregation, which is clinically relevant in diseases affecting blood viscosity. Lotions and creams are formulated with yield stress to stay on skin without dripping while spreading easily during application. Drilling muds used in oil wells must have sufficient yield stress to suspend rock cuttings when circulation stops, preventing them from falling back down the well. Landslides and snow avalanches are natural examples of yield stress fluids transitioning from solid to liquid behavior when critical stress is exceeded. Modern rheological characterization uses sophisticated techniques to fully characterize materials like ketchup. In oscillatory tests, we apply sinusoidal strain and measure the stress response, separating elastic and viscous contributions. Laos tests use large strain amplitudes to probe nonlinear behavior, revealing how the material structure breaks down during cycling. Extensional tests measure resistance to stretching rather than shearing, important for understanding behavior during pouring and dispensing. By tracking embedded tracer particles, we can visualize velocity fields and identify regions of high and low shear within flowing ketchup. Let me now synthesize everything we've learned into a complete physical picture of ketchup's behavior. First, ketchup has a yield stress of approximately 50 pascals arising from its complex microstructure of particles and polymers. Below this threshold, ketchup behaves as a solid and will not flow, no matter how long you wait. Above the yield stress, it flows as a shear-thinning liquid, with viscosity decreasing dramatically as shear rate increases. This combination of yield stress and shear thinning creates the characteristic all-or-nothing dispensing behavior that makes ketchup frustrating. Temperature affects molecular mobility, time-dependent thixotropy causes gradual structure breakdown, and formulation determines all quantitative parameters. Understanding these principles enables us to rationally control ketchup's behavior through optimal dispensing techniques and formulation choices. I hope this lecture has given you appreciation for the rich physics hidden in everyday materials. Ketchup appears simple, but its behavior emerges from a beautiful interplay of particle mechanics, polymer physics, and continuum fluid dynamics. By quantifying yield stress, shear thinning, and their microscopic origins, we transform a frustrating kitchen experience into a solved engineering problem. The same principles govern countless other materials, from industrial slurries to biological tissues to geological formations. Rheology, the study of flow and deformation, is a fundamental discipline connecting molecular structure to macroscopic behavior. Thank you for joining me in this deep dive into the rheology of ketchup. I hope you'll never look at a ketchup bottle the same way again.